So, today we're diving into something really cool from DeepSeek AI that could completely change the game for how artificial intelligence processes huge amounts of text. We're talking about one of the biggest problems for large language models. How do you get them to read something super long, like a novel or a massive report, without breaking a sweat?
So let's just start with this wild idea. What if an AI could just gulp down an entire book? Not word by word, line by line, but by just looking at it all at once, almost like it's just seeing a photo. I know it sounds a little like science fiction, but that's the core idea we're going to unpack.
But, before we get to the crazy solution, we really need to get why there's a problem in the first place. For all the amazing things AIs can do, they actually have a major reading problem. When you hand them something really long, they tend to slow way down.
And here's why. It all comes down to a massive computational roadblock. See, for most AIs, the time and the money it takes to process text, well, it doesn't just double if the text is twice as long. It grows exponentially. So reading 1,000 pages isn't just 1,000 times harder than reading one page. It's so much slower and more expensive that for a lot of things, it's just not practical at all.
Okay, so let's get into the solution. You know that old saying, a picture is worth 1,000 words? Well, the researchers here basically took that literally. The big idea is to turn thousands of words, or what the AI sees as text tokens, into a much smaller number of vision tokens, which is just an AI's way of seeing a picture.
And that brings us to this key concept, optical compression. You take a whole bunch of text, you turn it into a single dense image, and then you have the AI read the image instead of the text. It's kind of like shrinking an entire library's worth of books into one super condensed photo album that an AI can just flip through in an instant.
And the results? The efficiency gain here is just staggering. The researchers found they can compress text by a factor of 10. Think about that, turning 10 chunks of text into just one visual chunk. And here's the kicker. They can do this while keeping the accuracy incredibly high.
So how does this actually work? This isn't just some theory. They've built a working system to do this. It's all built around a technology called DeepSeek OCR. Now, OCR stands for Optical Character Recognition, basically teaching a computer to read text from an image. And this system is built from the ground up for this brand new way of reading.
So DeepSeek OCR has two main parts. First, you've got the DeepEncoder, which you can think of as the system's eye. Its job is to look at the page of text and squeeze it down into that compressed visual format. And then you have the language decoder, which is like the brain. It takes that compressed image and translates it back into language it can understand.
And the eye, the DeepEncoder, is really clever. It works in 3 steps. First, it scans the page in super high resolution, kind of zooming in on all the little details so it doesn't miss anything. Then, it squeezes all that information down, compressing it by a factor of 16. And finally, it zooms back out to look at the whole compressed page at once, to understand the big picture and how all the pieces fit together.
Okay, so that all sounds great on paper, right? The theory is cool, but does it actually work? Well, the team put DeepSeek OCR through its paces to see how it holds up in the real world.
And the results were pretty remarkable. When they compressed the text by 10 times, the model was able to reconstruct the original with an incredible 97% accuracy. And even when they pushed it to a 20x compression, it still managed 60% accuracy, which honestly is pretty amazing when you think about how much data it's throwing away.
Right, but that was a clean, controlled test. What happens when you throw some messy, complicated, real-world documents at it? To find out, they put it head-to-head against some other top models on a benchmark made for just that kind of thing.
And this is where you really see the magic of its efficiency. DeepSeek OCR actually performs better than a model like Menaru 2.0 while using almost 10 times fewer vision tokens to do it. It's not just better, it's smarter and way more efficient.
Okay, but this is where it gets really interesting. This is bigger than just reading documents faster. This whole idea could open up some really profound new paths for the future of AI itself, especially when it comes to how an AI might remember, and maybe just as importantly, how it might forget.
This is where things get a little mind-bending. The researchers themselves suggest that this technique could be used to create a memory system for AIs that acts a lot more like our own. Recent, important stuff stays crystal clear, but older, less critical memories get more and more compressed, and they naturally start to fade.
Just imagine it. For an AI, a conversation from right now would be perfectly clear. A week ago, still pretty sharp, but a memory from a year ago, it gets a little blurry. 10 years ago, it's almost gone. By squishing these older memory images more and more, an AI could actually simulate forgetting.
and save a ton of energy in the process.
All right, so let's just quickly tie this all together. What are the big takeaways? 1. AIs really struggle with long documents. It's just too slow and expensive. 2. This idea of optical compression, turning text into pictures, can make the process 10 times more efficient. 3. DeepSeek OCR proves that this isn't just a theory. It works, and it works really well. And 4, maybe the most exciting part, this could be a step toward AIs that have a memory that feels a lot more human.
And all of this leaves us with one last fascinating question to chew on. We spend so much time and energy teaching AIs how to learn and how to remember. But if an AI can learn to compress its own past into a blurry image, maybe the next big thing is teaching it the subtle and very human art of forgetting.